Hello, and welcome to this presentation, Understanding HF Propagation. In this presentation, we'll introduce you to the basic concepts of HF propagation and explain how HF propagation is influenced by solar activity. HF stands for high frequency and is usually used to refer to frequencies in the range of 3 MHz to 30 MHz, although in many cases the practical definition of HF can be extended down as low as 1.5 MHz. This corresponds to wavelengths in the range of about 100 meters to about 10 meters. You'll sometimes also hear HF referred to, albeit somewhat imprecisely, as shortwave. The primary use of HF is for long-distance or even global communications. Broadcasters can reach listeners around the world using HF, and this global reach is also useful in many government and military applications. Amateur radio operators around the world also frequently use and experiment with HF. And as we'll see in this presentation, it's the unique properties of HF propagation that enable long-range communications or even global communications. Although propagation at HF can provide worldwide communications, HF propagation can also be highly variable compared to communications at other frequencies, such as at VHF and higher. As a practical matter, this means that the greatest challenge in HF is finding the optimum frequency for communicating with an intended destination under the current propagation conditions. Before we go into more detail about how this is done, let's briefly cover the three main HF propagation modes: line of sight, ground wave, and sky wave. Line of sight is fairly easy to understand. Signals propagate in a straight, unobstructed path between the transmitter and the receiver. Line of sight is the only HF propagation mode which is fairly constant. Your ability to use line of sight to communicate with another station at a given location doesn't change much over periods of minutes, hours, days, months, years, etc. That said, HF isn't a very good choice for line-of-sight communications, and it's rarely used for this purpose. Because of the lower frequencies, HF requires large antennas, and bandwidth is also somewhat limited. There also tends to be much more noise at HF compared to higher frequencies. This can be a problem because the limited bandwidth at HF usually means communications are carried out over AM or single sideband, which are much more sensitive to noise than wider bandwidth FM. For these reasons, most line-of-sight communications are carried out at VHF or higher, not at HF. If we don't have a direct line of sight to another station, ground wave is a possible solution. Ground wave, sometimes called surface wave, involves signals propagating along the surface of the Earth. Interaction between the lower part of the transmitted wavefront and the Earth's surface causes the wave to tilt forward, allowing the signal to follow the curvature of the Earth, sometimes well beyond line of sight. Ground wave propagation is, however, highly dependent on two different factors: the conductivity of the surface and the frequency of the transmitted signal. In general, higher surface conductivity gives better results in the form of greater distances that can be covered. Salt water has excellent conductivity, especially compared to dry or rocky land, so ground wave is a good choice for ship-to-ship or ship-to-shore communications. With regards to frequency, ground wave works best for lower frequencies. For example, the theoretical range of a 150-watt transmitter at 7 MHz is 35 kilometers over land and close to 250 kilometers over the sea. At 30 MHz, however, our range falls to only 13 kilometers over land and just over 100 kilometers at sea. One of the most important propagation modes of HF is skywave, because it's skywave propagation that enables beyond line of sight or worldwide communications. In skywave, layers of ionized particles in the upper atmosphere refract HF signals back towards the Earth, allowing communications over many thousands of kilometers. The distances that can be covered by different frequencies are almost entirely a function of the state of these layers of ionized particles, collectively referred to as the ionosphere. In this presentation, we'll explain the different layers of the ionosphere, how the ionosphere is affected by the sun, and how we can both quantify the current state of the ionosphere and predict the future state of the ionosphere. The incident angle, or the angle at which a signal reaches the ionosphere, also plays an important role in how far a skywave signal will propagate. The radiation angle of an antenna is primarily a function both of the type of antenna and the location at which the antenna is installed. Higher placement of an antenna usually lowers the radiation and incident angles. And generally speaking, the lower the incident angle, the greater the distance that is covered by skywave propagation. Note, however, that so-called skip zones may be created depending on radiation or incident angle. In these zones, HF signals can't be received either via skywave or via ground wave propagation. In order to understand skywave propagation, we should start by explaining how ionization occurs in the Earth's atmosphere. When ultraviolet energy or radiation from the sun strikes gas atoms or molecules in the atmosphere, this energy can cause electrons to become detached. The result is a positive ion and, more importantly, a free electron. The Earth's magnetic field keeps these free electrons roughly in place. The level of ionization and the number of free electrons increases as the amount of sunlight striking a given part of the atmosphere increases. When that part of the atmosphere rotates away from the sun, that is, at night, the energy is removed and the ions recombine to form electrically neutral atoms or molecules. Note that recombination is a slower process than ionization. Atmospheric ionization increases rapidly at dawn, but decreases less rapidly after dark. As mentioned earlier, the region of the Earth's atmosphere that undergoes this ionization is collectively called the ionosphere. The level or density of ionization in the ionosphere is different at different altitudes, and areas with ionization peaks are often grouped into so-called layers or regions. The layers that are important for HF propagation are the D layer from 60 to 100 kilometers, the E layer from 100 to 125 kilometers, and the F layer or layers from about 200 to 275 kilometers. Note that these are only rough numbers. The thickness and altitude of ionospheric layers is never constant. The reason for defining these different layers is that each of these layers will refract and or absorb HF signals in different ways. It's important to note that the ionosphere does not reflect signals, but rather refracts signals. The different electron densities at different altitudes is what makes this refraction possible. Let's start with the lowest level of the ionosphere, the D layer. The D layer only exists during daytime hours and disappears at night. Although the D layer is ionized by solar radiation, the density of free electrons in the D layer is too low to effectively refract HF signals, and therefore the D layer cannot be used for skywave propagation. Instead, the D layer acts as an absorber of HF signals. This absorption is higher for lower frequency signals than for higher frequency signals. Absorption also increases with increasing ionization, so absorption is usually highest at midday. For these reasons, the properties of D-layer absorption mean that higher frequency HF signals work better during the daytime, whereas lower frequency signals work better at night, after this layer has disappeared. The next highest layer, the E layer, is the lowest layer of the ionosphere that can refract HF signals back towards the Earth, and is the lowest layer that supports skywave propagation. Compared to the other layers, it's relatively thin, usually around 10 kilometers or so. The E layer is much more dense, that is, ionized, during the day, but unlike the D layer, it doesn't completely disappear at night. Aside from mostly short-range daytime communications and a few other special cases, E-layer propagation is not commonly found in HF. Note, however, that at VHF, the E-layer is very important and supports some rather exotic and less predictable propagation modes, such as sporadic E, that make long-distance communication over thousands of kilometers possible, even at the relatively high frequencies of VHF. The F layer is the most important for skywave propagation. During the day, the F layer splits into two sublayers, F1 and F2, which merge back into a single layer again at night. Compared to the D and E layers, the height of the F layers changes considerably based on things such as time of day, season, and solar conditions. More on this shortly. The lower F1 layer primarily supports short to medium distance communications during daylight hours. The F2 layer, on the other hand, is present more or less around the clock. It has the highest altitude and the highest ionization of all the layers, and therefore is responsible for the vast majority of long-distance HF communications. The degree to which the different layers of the ionosphere refract and or absorb radio frequency signals is largely a function of that signal's frequency. The general rule for HF skywave communications is to always use the highest possible frequency that will reach a given station or destination. This is called the maximum usable frequency, or MUF. Signals whose frequencies are higher than the MUF will not be refracted by the ionosphere. Usually, the MUF increases with increasing ionization. Another important frequency threshold is something called the lowest usable frequency, or LUF. When the signal frequency is at or below the LUF, communication becomes difficult or impossible due to signal loss or attenuation. So we want to choose a frequency that's somewhere between the LUF and the MUF. There is one very important difference, though, between MUF and LUF. Because the LUF is mostly determined by noise, using higher transmit powers, a better antenna, etc., can improve or lower the LUF. MUF, on the other hand, is entirely a function of the ionosphere. You can't improve or increase the MUF by using more power or a better antenna. The MUF simply is what it is. And as we'll see shortly, if the LUF becomes greater than the MUF, no HF communication is possible. One way to determine the MUF is purely through experimentation, but there are also methods for estimating the MUF using something called the critical frequency. The process for measuring the critical frequency is as follows. Pulses at various frequencies are transmitted vertically by equipment called ionosondes. Depending on the frequency of the pulse, these pulses are returned by different layers of the ionosphere, and we can use the return time to estimate the heights of the different layers. Once we reach a certain frequency, the pulses are not returned by the ionosphere, and instead continue on into space. This is the critical frequency. Critical frequency is a function of both the current ionization level as well as the measurement location. It's measured regularly at hundreds of locations around the world. Mathematically speaking, the maximum usable frequency is the critical frequency divided by the cosine of the angle of incidence. If we send a signal straight up at 90 degrees, MUF and critical frequency are the same. But as a practical matter, the maximum usable frequency is usually estimated at 3 to 5 times the critical frequency. Critical frequency is one way of quantifying the state of the ionosphere, but it is an active test. We transmit signals and measure the return signals. In addition to critical frequency, there are 3 common passive methods that can be used to quantify the state of the ionosphere. The first of these is sunspot number, which can be used to predict the level of atmospheric ionization. The second is the solar flux index, which is an actual measurement of ionization. There are also 2 geomagnetic indices, the A index and the K index, which give an indication of the impact of solar particles on the Earth's magnetic field. Taken together, these quantities provide a good indication of the current state of the ionosphere and can be used to predict HF propagation. Let's take a look at each of these 3 quantities in a bit more detail. Sunspots are, relatively, cooler surface regions of the Sun. Relatively in this case means they have temperatures of about 3000 Kelvin versus the normal 6000 Kelvin seen elsewhere. After they appear, sunspots last between a few days and a few months. Sunspots are associated with powerful magnetic fields, and these fields affect how much radiation is given off by the Sun. The greater the number of sunspots, the higher the level of solar activity and radiation. And because of this, more sunspots generally means higher atmospheric ionization, a higher MUF, and better overall HF propagation. The quantitative measure of sunspots is sunspot number, which is a daily measurement of sunspots. Note, however, that sunspot number isn't simply a count of the number of sunspots. It also takes into account additional factors like the size and grouping of sunspots. Sunspot number is recorded by a number of solar observatories around the world, and sunspot number values range from 0 to a maximum recorded value of about 250. As mentioned a moment ago, more sunspots, or a higher sunspot number, almost always means better HF propagation. It's also worth noting that sunspot data have been collected for almost 400 years, giving us valuable information on how the number of sunspots changes over time. And sunspot numbers do change over time. In fact, sunspot activity follows a roughly 11-year solar or sunspot cycle, as shown in this graph. Generally speaking, sunspot numbers are usually around 150 at the peak of a cycle, during which time HF propagation is very good on most frequencies, including higher frequencies. At the bottom or trough of the sunspot cycle, sunspot numbers close to 0, meaning much poorer HF propagation. Given the period of the sunspot cycle, it should be clear that sunspot cycle is only good for predicting long-term HF propagation, that is, in terms of years, and over this time period it is fairly reliable. It's also, however, worth noting that at several points in history, for example in the late 1600s and the early 1800s, sunspot numbers stayed low for several decades, creating so-called minimums or minima with very little solar activity. The reasons for these minima are still very much a mystery. We can also quantify solar activity by measuring the level of solar noise, or flux, at a frequency of 2800 MHz. These measurements are reported as the solar flux index, with values given in so-called solar flux units. Measured solar flux values generally fall in the range of about 50 during a solar cycle minimum to about 300 during a solar cycle maximum. Since solar flux is a measurement, not an observation, it tends to be more consistent and reliable than sunspot number, but it also doesn't have the same 400-year history of values. However, solar flux values tend to correlate quite well with sunspot numbers. Like sunspot number, higher values of solar flux mean higher maximum usable frequencies and better HF propagation. Sunspot number and solar flux index are valuable measures of longer-term variations in solar radiation. The ionosphere is also affected by shorter duration events occurring on the Sun. The most important of these are solar flares, which are a type of eruption on the surface of the Sun. Solar flares cause a rapid rise in both X-ray and ultraviolet radiation, as well as the ejection of both low and high-energy particles. Solar flares are essentially unpredictable, but they do occur more commonly during peaks in the 11-year sunspot cycle. Solar flares have a significant effect on HF propagation because they can lead to sudden ionospheric disturbances, polar cap absorption, as well as both geomagnetic and ionospheric storms. As the name implies, a sudden ionospheric disturbance is sudden. It occurs about 8.5 minutes after a flare, that is, at the same time the flare becomes visibly detectable on the Earth, and is caused by the arrival of solar radiation. This radiation causes D-layer ionization, and hence D-layer absorption, to increase rapidly, starting at the lower frequencies and moving upwards. The affected frequencies are often almost completely blacked out. Fortunately, a sudden ionospheric disturbance only impacts the sunlit hemisphere, and tends to last a relatively short time, typically an hour or so. And in some cases, smaller solar flares can actually enhance HF propagation by increasing ionization at higher frequencies without a corresponding increase in D-layer absorption. The next effect of a solar flare is something called polar cap absorption. The high-energy particles emitted by a flare reach the Earth several hours later, and the Earth's magnetic field prevents them from entering except at the poles. When they enter the atmosphere, these particles can increase D-layer absorption in the polar regions, and this effect can last for several days. During this time, HF signals traveling through or near the poles will be blocked by this increased attenuation, but paths that do not go near the poles may remain relatively unaffected during this event. Geomagnetic storms are caused by lower energy particles arriving at the Earth. This occurs 20 to 40 hours after a solar flare. These particles can also be generated during something called a coronal mass ejection, which can occur independently of a solar flare. In either case, these particles can cause geomagnetic storms. Geomagnetic storms produce visible aurora, but they also can interfere with GPS signals, satellites in general, terrestrial power distribution networks, etc. Geomagnetic storms don't directly interfere with HF propagation, but they can create ionospheric storms. Ionospheric storms lower the maximum usable frequency and degrade HF propagation. And as mentioned earlier, if the MUF becomes higher than the LUF, an ionospheric storm can create a complete HF skywave blackout. One final note. It's possible to have a geomagnetic storm without an ionospheric storm, but the converse is not true. All ionospheric storms start out as geomagnetic storms. Sunspot number and solar flux index can be used to quantify ionospheric conditions, but to quantify geomagnetic conditions we use A and K indices. In general, lower values for A and K mean a more stable ionosphere, although, as we just mentioned, in some cases a geomagnetic storm may not lead to an ionospheric storm. A and K are measured at observatories around the planet, and these local values can be averaged to produce planetary values. One of the biggest differences between these two indices is that A is calculated daily, whereas K is measured every 3 hours. Higher values of K indicate a current or ongoing geomagnetic event, whereas A is useful in knowing how long this disturbance has been occurring. Let's summarize what we've learned. Global HF communications are usually based on skywave propagation rather than on direct line of sight or ground wave propagation. In skywave, signals are refracted by the ionosphere, although the effect of some layers is more to absorb signals than to refract them. Whether or not a signal is refracted or absorbed by the ionosphere is largely a function of 3 things: the frequency of the signal, the incident angle, and the amount of ionization in the upper atmosphere. Generally speaking, this ionization increases during daylight hours while the sun is illuminating that side of the Earth. On a longer time scale, ionization also increases as the number of sunspots increases, the number of sunspots following a roughly 11-year solar cycle. Aside from these semi-regular effects, certain types of solar events can unexpectedly or unpredictably disrupt the ionosphere and hence HF propagation. Solar flares are the most common of these, and flares can lead to so-called sudden ionospheric disturbances, polar cap absorption, and both geomagnetic and ionospheric storms. Coronal mass ejections are less common, but often a more severe, source of geomagnetic storms. And finally, we can quantify the current state of the ionosphere and/or make predictions about HF propagation based on measurements such as sunspot number, solar flux index, and the A and K magnetic indices. This concludes our presentation, Understanding HF Propagation. Thanks for watching.